Hello class, welcome to today's lesson. And in this lesson, guys, we're gonna continue with the stage 2, now with the basic concepts of dynamics. If you remember at the very beginning of this stage, I told you that mechanics, which is what we are studying, the science of motion, mechanics, is divided into kinematics and dynamics. And kinematics did not pay attention to the causes of motion, and dynamics is actually the opposite. This branch of mechanics actually cares about the causes of the motion of the bodies. So we're gonna now study a little bit, or well, the basic concepts behind dynamics. That's what we're gonna do today. And we're gonna go over these 4 points. We're gonna study what inertia and mass are. We're gonna study the concept of force, the different types of forces in nature, and finally, I need to explain to you the difference between mass and weight because most people think they are the same. Mass and weight, they're not the same, guys. Completely different stuff. So let's begin. So first, inertia and mass. What is inertia? Let's read the definition. Inertia is the tendency of all bodies to continue moving the way they were moving unless a force acts upon them. And that's what we understand by inertia in everyday life. I don't know if you have heard this word in other contexts, like maybe not scientific contexts, but we often say that things have inertia when they have a tendency to remain in the same way that they were. Okay, for example, if you're a I don't know, if you don't like to do a lot of stuff, like you are a little lazy, because of the inertia, you will continue being lazy, or you will continue to procrastinate. Have you noticed that? And on the opposite side, when you start doing a lot of stuff and you start having a very active life, it is most likely to continue in that path. So the inertia also applies in other fields of life. So how does inertia look? How does this property of the bodies, this tendency of the bodies look? How does this look? It looks like this, guys. Just observe this animation. We have a trampoline. We have some clay in here. And look at what's happening. At the beginning, right there, the clay is at rest, right, upon the trampoline, upon the surface. And when this person uh, jumps on it, on the trampoline, what you're going to observe is that the clay has a tendency to remain where it was. Can you see? It wants to remain in the same place right there, and then it's going to come down. Okay? Like it remains there, and then it goes down. Okay, why? This is what we call inertia. It's the tendency of anybody to remain doing whatever they were doing unless a force starts to act on them. So why does the clay go downwards? Like right now, can you see? Well, because at the moment that there is no trampoline placed below this clay, the the influence of the earth, of gravity, starts to being felt by the clay, and so it's gonna go downwards. You see, like that. That's inertia. Same idea. Look at this animation. This one looks very very good. Same idea. Look at the leaves. Can you see how they remain on place at rest, and then immediately they go down because now they start to feel gravity, and gravity is gonna pull downwards. And it's not that gravity is not present right there at this point. Gravity is present always. Okay, like at this point, gravity is already present on the leaves. So why are the leaves not going downwards? Because there is this net below them, which is, let's say, equilibrating the influence of gravity. When there is no more net, gravity acts completely on the leaves and they start moving downwards or accelerating downwards. So that's inertia. That's how inertia looks. We've all experienced the next animation I'm gonna show you. It's a little, let's say, aggressive, I guess, because we have all experienced the following. We have all experienced being on a car, and then suddenly the car brakes, and you're gonna go like, you're gonna experience this motion, right? When the car brakes, you're gonna go forwards. You're gonna keep on moving in the same way you were moving. At this point, this stick figure right there is moving to the right, and when the car stops, the body of this stick figure will want or will tend to move rightwards until some force stops it. In this case, the force of the windshield. So this next animation I'm going to show you, it's a little rough, but it's just to show you how dangerous inertia is when driving. Look at this. It's pretty harsh. It's a bus. The bus is going to brake, and just take a look at that, guys. Okay? Look at all the people. When the bus brakes, all these people which are moving in this direction will want to continue in that direction because of the inertia. The inertia of all of these bodies will tend to move the body in the same direction until they face an opposite force, in this case the chairs. So let's suppose they were going at 50 kilometers per hour. When the bus brakes, all these bodies will continue moving with the same velocity, 50 kilometers per hour. You see, so that's how dangerous driving is. Without seat belts, the driving is a dangerous business. It's extremely, extremely dangerous, and we're often not conscious of these things. It's very, very important, guys, to understand how the world works. Okay, so that's inertia. It's just a tendency of bodies to continue moving the way they were moving. And what's mass? Mass is a quantitative property of a body. And now I'm going to tell you what I consider a very difficult explanation of what mass is, at least at this point in high school, because all that you've been told about mass is that it's just how much matter there is on a particle. But that's not a good definition. It's not a definition in physics. That's not what we understand by definition. Because that definition, I'm going to repeat, mass is the amount of matter that there is in a body. That definition doesn't allow you to measure anything. So it doesn't allow you to measure mass. Okay? That's not a good definition in physics. And it's just a partial definition when you are, little kid. It's okay for that for some purposes, but it's not a definition. So what is the definition of mass? Well, it's the following. Mass is something that quantifies the amount of acceleration a particle will experience when we apply a force on it in relation with the acceleration produced by the same force on a particle of unit mass. I know that you you probably did not understand anything about what I just said. It's complex, so I'm gonna try to explain to you using the pencil. So the mass m of a particle is defined operationally as follows. So let's do this, guys. This is gonna be a little complex. I'm gonna test your ability to understand difficult concepts. So let's see. It works in this way, guys. You have a particle. I'm gonna just draw a box. And this particle has a mass m that we don't know. We don't know the mass of this particle. We want to measure it, or we want to calculate the mass of this particle. The experiment that we have to perform in order to assign mass to this particle is the following. You do this first. You're gonna choose any object, and you're gonna call it the reference. Okay, this is the body. Let me draw this a little larger. Okay, We're gonna say that this other particle has a mass of unit 1, okay? I'm gonna call it M1. So this is the unit mass, la masa unitaria. So the unit mass, by definition, is equal to 1. By definition, because we said so. Okay, this is our own arbitrary choice. We say, okay, I'm going to choose this object, and I'm going to say that this has a mass of 1, by definition, because I say so. Now, in relation to the mass of this object, I'm going to find out the mass of this other object. Like, could this mass be twice as this? Or could this mass be 3 times as this? Or could this mass be 1/2 of this, etc.? How do we find out? How do we find that out? What we do is this. We're going to apply, now that I have these two masses laid down, we're going to apply the same force on both of them. The same force, exactly the same force. And as a result, what I'm going to observe, and perhaps you're wondering what's going to happen, well, the force will cause an acceleration of this particle and on this particle. In other words, these forces, well, this same force will change the velocity of both particles. It's going to accelerate both particles. So this particle will accelerate with an acceleration that I'm going to say is A, and this particle will accelerate with an acceleration that I'm going to call is A1. I'm going to call it A1. Acceleration and acceleration 1. Okay, with some clock and with some measuring tape and doing very precise measurings, we can actually measure this acceleration, guys. We can measure it, and we can measure the acceleration of this other object. So I have this value, I have this value, and by definition, I have this other value. It's 1 by definition. So I know A, I know the acceleration 1, and I know the mass 1, which is equal to 1. Okay, now with these 3 quantities, I can find the magnitude of this mass m, which is unknown at this time. And that's going to be defined with the following equation. The relation of this mass to this one, the relationship or the ratio of this mass to this one, the ratio, is going to be the same as the ratio between these two, but inverse. Like the ratio of this mass to this mass is equal to the ratio of these two masses, of these two accelerations, but inverted, like so. A1 over A. So the ratio of the mass, the unknown mass, to the unit mass is equal to the acceleration of the unit mass to the acceleration of the mass unknown. You see? And when you isolate the mass that we wanted to know, which is m, you're going to get this, that m is equal to A1 over A times the mass 1. Do we know A1? Yes, because we measured it. Do we know A? Yes, because we can measure it with clock and measuring tape. And do we know M1? Yes, because it's just 1. So therefore we can find the mass of this other object. Okay, that's how it works. Now you may be wondering, why is this equation the way to go? Like who came up with this? How do we know this is the right equation? Okay, let me tell you why. What we want to say when we define mass is the following. I want to say this, that if this mass and this mass are being subjected to the same force, and let me raise, well, yeah, let me raise this, and this. And let's suppose these two masses under the same influence, under the same force, what we find out is that the acceleration of the unit mass is, let's say, 1. And yet the acceleration of this other mass is 1/2. Okay? What I want to say is that this mass is twice as this one, because it accelerated half as this one. You see? What I want to say is that the greater the mass, the greater the mass of an object, the greater the mass, the less the acceleration. That's what I want to um, that's what I want to say as a scientist. If this is twice the mass of this, it will accelerate half as much as this one. Okay, and the only way in which you can make this work is through this equation. Okay, if this is twice as this, then the ratio of this to this should be equal to 2, and therefore this ratio should be equal to 2. And the only way you can get that 2 as an equation is by dividing a1, which is this number, over this other one. When you divide 1 over 1/2, you're gonna get 2. So they are inversely proportional. The ratio of this to this is inversely proportional to the ratio of this and this. I know this is quite complex. I just wanted to mention that there is in fact a quantitative way to measure mass, and it's through this experiment. Okay, so let's continue. Now, what is force? So force is any influence applied on a particle that will make it accelerate. It's that simple, guys. For example, look at this. We have a foot and a soccer ball. If you consider your particle of study, the ball, and if you hit it with the foot, you're gonna cause an acceleration of the ball, right? Because the ball is at the time is at rest, and when the foot comes and kicks it, it's gonna accelerate. It's gonna change the velocity of the ball. So basically, what we say is that the foot is applying a force on this particle, which is the ball. You see? Now look at this other image. What do we have? We have the Earth and Mars and the same person on top of them. So in this case, uh, how is the force involved in this image? Well, what we say is that both the Earth and Mars are applying forces on these bodies, and those forces are being directed towards the center of both planets. Okay, so in here you may not see acceleration when the body is at rest on the surface of the planet. You will not see acceleration, right? But what happens when you I don't know, when you are hiking on a mountain and then you, I don't know, you fall down, you're gonna observe that acceleration towards the surface of the earth. Okay, or if you jump from a building or something, you will experience that acceleration. The fact that these people can be at rest on top of the surface is because there is another force applied upwards on them, which is caused by the ground, and it's gonna let's say equilibrate the force applied by these two objects, the Earth and Mars. So basically, force is any influence applied on a particle that will make it accelerate. And forces are applied on particles by other particles. Whenever you talk about force, you need to say like what particle is being subjected to that force and what particle is producing that force. So in this case, I have a force being applied on the soccer ball by the foot. In this case, there is a force being applied on the person by the earth. You see, you always have to say on what particle is the force being applied and by what other particle. Let me show you some other ideas that will make you understand this. Look at this. We have a magnet and we have some metal bearing balls. You see? So is this magnet applying a force on this star made of bearing balls? Yes. Why? Because as we can see, this object is influencing the star, and it's going to accelerate all the particles that made up the star. Can you see? So in this case, we say that there is a force being applied on the star by the magnet. There is a force applied on the star by the magnet, and we can say that because we can see that the star is accelerating At first it's at rest, and then it's moving to the right. It changes the velocity of the star. Same in here. Electrostatic repulsion, where you have two electrons. You have been told that when you get them close together, they're going to repel each other, right? So it's the same here. They're both applying forces on each other. This applies a force on this, and this applies a force on this. And therefore, they're going to accelerate. They're going to change their velocities. Okay. So that's what a force is, guys. It's basically something that makes a particle accelerate. So what types of forces are there in nature? We have gravitational forces like the ones I told you in here, the ones produced by mass, the mass of mostly large objects, although any object can produce gravity. Even a soccer ball, it has some gravity, etc. It produces gravity, but the influence is perhaps better known when we consider large objects as planets or stars, etc. We have electromagnetic forces due to electric charges, and we have other types of forces such as nuclear forces, the ones that go inside the atom. Now let me tell you a little bit about the difference between mass and weight. First of all, they're not the same. They are not the same. What is the difference? Okay, same image that I showed you a moment ago. We have the Earth and Mars, and we have the same person. Let's consider the same person is laying on the surface of both planets. So the mass of this person, guys, doesn't change. It's going to be the same both on Earth or on Mars. It's going to be 50 kilograms, let's just say. The weight, though, the weight is going to change. And by the way, ignore this because this is in English units. We don't really use that in physics. Well, we use them, but it's not proper. We use newtons. Okay, so what is the mass? The mass, like I told you guys, is a property inherent to the body itself. Okay, the mass is not going to change. The thing that is going to change is the weight of this person. Why? Because the weight is just the force. Weight is a force. You have to understand that. Weight is a force. And that force is produced by these planets, by the Earth or by Mars. It's being applied on this person, and it's being directed in this direction towards the center of the planet. If the person was over here, then the force would be directed in this direction. Okay, and weight can vary or can change according to how much mass there is on the planet. That's why on Earth you will have more weight than you would have on Mars, or that you would have on the moon. If you put a person on the moon, this person would have much less weight than on Mars or than on Earth. Okay, the force that the moon will apply on the person is going to be less than in these two cases, and that's why you can observe these animations of people on the moon. Let me try to get one. Like they can jump very high. Jumping on the moon. They can jump quite high. And the reason is because there is less weight. The moon is not attracting you with as much force as the Earth does because the moon has less mass. Well, in that case, it's appreciable, right? It's actually noticeable. That guy's gonna fall down. And you have to consider this. These guys are jumping with all of this equipment, which weighs a lot. All of this, the astronaut suit and all these backpacks, etc. They weigh a lot. I don't know how much, but they must be in the, I don't know, in the 60 kilograms or something like that, 50 kilograms, I believe. I don't know if I'm mistaken, but that's my guess. Look at that. That would be impossible to do on Earth. considering that you're wearing a suit and a backpack which weigh a lot. That would be impossible. And these guys can do it without much problem. And can you see how much they remain on the earth? Well, there's nowhere here, but okay. So that happens, guys, because the moon produces less weight on you than than if you were on Earth. So the weight can change, guys. The weight can change. You're gonna have more weight on more massive planets, but your mass will remain the same. Your mass always remains the same. And another difference is that the mass of an object, sorry, the mass is just a scalar. It's a scalar quantity. If you remember, a scalar quantity does not have direction. It just has a magnitude, 50 kilograms. That's it. And the weight, though, the weight is a vector. Remember that a vector has both magnitude, or how strong it is. Can you see? In this case, it's stronger than in here. But they also have direction. The weight has direction because it's a force. And in this case, for this particular person, that vector goes in this direction and in this other direction. But if I put you in another place on Earth, in here, that vector will have this other direction. You see? So the directions are different. So that's another of the differences. This is a scalar, mass is a scalar quantity, and weight is a vector quantity. Mass cannot change, okay, and weight can change according to what place you're in. So that's a little bit about the difference between mass and weight. That's why when you ask the question, what is your weight? What is your weight? Like, ¿cuál es tu peso? Or how much do you weigh? How much do you weigh? That's not really what you're asking, guys. That's not what you want to ask. What you should ask is, what is your mass? What is your mass? That is the proper question, although nobody uses it, right? We always say this, what is your height, or how much do you weigh? We never say what is your mass. But this is actually an incorrect question. We're not looking for this. We're looking for the mass of the person, not for the weight. Okay, let me stop it right there, guys. Let me go back with you.